Okay, thank you very much. And thank you for the invitation to speak, and thank you guys for coming. So my name is Matt McCauley. I'm at Clemson University in South Carolina, and I'm going to talk about Cayley diagrams with more of a focus on undergraduate and graduate abstract algebra rather than the research side of that, which is a fun topic on its own. Cayley diagrams are fundamental in geometric group theory, which is an area of mathematics where you build where you study groups by looking at geometries or spaces that act on nicely. So what I want to do is convince you without a doubt why every algebra class should use Cayley diagrams fundamentally. So, so this image is called an ambigram. This is a term that Doug Hostetler came up with, and I think he just entered the chat. He's a Pulitzer Prize winning author. Some of you know him as the author of Gödel, Escher, Bach. And there's a fun history about my talk and these ideas that basically dates back to him about 20 years ago. So when he was on sabbatical in 2001, he explored idea of visual group theory and ended up teaching 3 classes on this in the early aughts. And one of the students, Nathan Carter, wrote a book called Visual Group Theory, which is a fantastic general audience book that was published in 2009. Some of you may be familiar with. And so my story was I met Nathan at MathFest, and I decided to try to teach abstract algebra the next year using those ideas. Now, I had to massively supplement this book because it was never written to be an undergraduate level book. So I've, over the course of teaching it many times, I've added and found a lot more examples to a place where I thought it was completely done. I would never change it in 2019. And then I said, you know what, there really should be a textbook. My students wanted one, so I decided to write one. And of course, in the process, I discovered dozens, if not hundreds of other visuals and ideas and filling in all the gaps that I didn't know existed. And now I don't even want to touch the way I used to do the course. So I decided to write so I have a book that's about 400 pages written, probably out of 600. And there's a lot of different visual techniques or objects that I use, not just Cayley diagrams, but cycle diagrams, Cayley tables, and subgroup lattices. But this talk is really just focused on Cayley diagrams because this is one of the most basic objects in I think. And what I want is I want people in 20 years, people born today in 20 years to say, taking algebra, to say to themselves, you know what? Can you imagine that 20 years ago, people didn't used to teach this, or this class used to be taught without pictures? Can you imagine that? To me, that's like teaching calculus without graphs, or as Doug has told me, it's like teaching crystallography without pictures. These are objects that have symmetries. You should show those pictures in any class. You know, you wouldn't teach art history without that. So I'm not trying to just sell the book that I'm writing. I'm trying to sell an idea. What I want is I want existing books to have to write new editions with visuals. I want every book in 20 years to have Cayley diagrams as an inherent part of them. And that's my goal. I want to convince you of that going forward. So this is this ambigram Doug Hostetler sent to me about a week and a half ago. It's if you turn it upside down, it's my name, and you can see he signed it with his name here. And if you turn that upside down, it's the year 2021. So this is something that has 180-degree symmetry, and symmetry is a big part of group theory. So I recognize actually a couple names. So I've given a talk on this a few months ago in Talk Math with Your Friends seminar, but it wasn't really, but there's going to be overlap, but this is going to be very different. So in that, I gave a whole bunch of visuals, especially subgroup lattices, and I talked about nilpotent groups and solvable groups and other things that really don't, visuals that weren't involving Cayley diagrams. Here, I'm really focusing on the Cayley diagrams, hence the name of the talk. Okay, so if you have questions, just feel free to interrupt me or probably won't be checking the chat because there's only like 2 or 3 things I can do at once. So let's get started. So a group presentation, as most of you know, and so if you don't know what a group is, I think you'll still get a lot of this along the way. but I'm going to assume that you know basically what a group is, or even if you can't define it, you know the general concept. So it's a presentation is a description as a list of generators and a list of relations. And you can think of the vertical bar as being subject to. So just as an example, the set of symmetries of a triangle, there's a lot of ways you can write this as a presentation. It's called D3, and it's generated by a reflection, like a 120 reflection, and this is a rotation and a reflection, and subject to these relations. So if you rotate 3 times, you get the identity. If you reflect 2 times, you get the identity. And then this is how the reflections and rotations are connected. So let me just put this picture up and say that this picture really encodes all of these presentations. And it's not an obvious problem of how to, or it's a hard problem to, given a presentation, figure out if this even is the identity or the trivial group or not. That's actually an uncomputable problem. That's a different subject for a different talk. But at the undergraduate and graduate level, these presentations, you can typically reconstruct the diagrams without much trouble. So what I want you to take away from this is a Cayley diagram is no more than a visualization of a group presentation. This encodes the same amount of information that any of these presentations do, really no more and no less, but it just allows us to visualize it easier. So I can see, for example, if I want to say what is R F times R, I should say throughout this talk, I will be writing left to right, not right to left like function composition, left to right like we read. So RF times R squared F, you start from the identity and you do RF, R squared F, and you get R squared. This is like a group calculator. It's really convenient. And I'm going to come back to this throughout. So you can also label Cayley. So in this talk, I'm going to go fast because there's not that many equations. There's going to be a lot of pictures. And I want to make sure I cover the stuff, and it will be recorded. So if you miss something, you can go back and catch it later. So you can label the nodes with configurations. So this just gives extra information. And here's a diagram as to, so that this I've labeled these with the 3 rotations and the 3 reflections, but you can think of the reflections as what they are, as reflections of the triangle about different axes. So again, we always multiply left to right. So the first half of this talk, I'm going to be showing off a ton of groups, because in most algebra courses, you learn about the cyclic groups, the dihedral groups, the symmetric groups, and alternating, and then maybe the quaternions, and that's about it for the finite groups. And using this approach, we can get through a lot more groups, a lot more examples. And it's so important to understand group theory, I think, to understand, to be intimately familiar with a lot of examples. And there's so much more you can do when you have not just a presentation, but a visualization of a presentation. So I will try to, when I draw Cayley diagrams, I try to put the identity where it would go in the unit circled. So you can think of like these as like so this is the symmetries of a pentagon. So you can think of these as the rotations of a pentagon. And you can think of these as reflections. So if I first flip horizontally and now I rotate, I go this way. Okay, so dihedral groups, you can also generate with reflections. So instead of generating with a rotation and a reflection, I can generate with this reflection and that reflection, because if you do those in either order, you get a rotation. So here's a Cayley diagram for this. This is sort of 2 different ways to see the dihedral group, the symmetries of the triangle. And this generalizes for any n. So there's also an infinite dihedral group. If you get rid of that relation that r to the n equals the identity, you get the infinite dihedral group. I'll talk more about this in a second. And this can also be generated by reflections as well. This is an example that usually does not come up in an algebra course, because it was just given by a presentation, and what are you going to do with this? So the quaternion group is something that does come up. So this is the group, many of you know this, I, J, K, so it's I, J, K, negative I, negative J, negative K, and plus or minus 1. So here's, I call this the Cayley, this is called a Cayley table. Here's a Cayley diagram. And notice that if you take this, let me use a different color. If you identify, or if you collapse this Cayley diagram, you say, let's collapse these things into a single node. What you get is you get this diagram here. And this is the Cayley diagram of the Klein-Ford group, the symmetries of a rectangle. And you can see this shrinkage in this table shrinking down to here, and this is called a quotient. So my students at the first week class, they understand what a quotient is before we ever get to the idea of a homomorphism or do it formally. And so this is something I can do because I introduced Cayley diagrams early. So now I also think it's important to understand that you can represent groups with matrices. So the cyclic group, I call it CN, some people call it ZN, but multiplicatively I like to call it CN, is generated by the group of, or generated by these n complex, or is the set of these complex reflections. So it's generated by a single reflection matrix. So you can think of this as a reflection matrix of complex reflection matrix of order n, and this swaps the coordinates, the first and second coordinates in C2. And if you put these together, they generate the relations are the same as the dihedral group. So you can realize the dihedral group via a representation generated by these two matrices. So here's an example of this for n equals 4. Now, the quaternion group can also be represented with matrices, and this is the matrix for I, and this is the matrix for J. And so I times J, so let me write this down. So you can think of this as I, you can think of this as J, and you can think of this as K, and I times J is K, J times I is negative K. And here's a different Cayley diagram for the quaternion group. I think it's incredibly helpful to see this picture rather than just I, J, and K. Now, here's a group that most of you probably did not learn about in your undergrad course. And my students, it is one of the fundamental examples that we do throughout. And I say that you probably didn't learn about it because I didn't learn about it in my courses either. So have you ever thought about taking the quaternion group and taking this matrix I, and this matrix for, this is for the complex number I, and what is I? I is the square root of -1, which on the unit circle is a root of unity. So what if you replace I in here with a different root of unity, like a 6th root of unity instead of a 4th root of unity? What would happen? If you do that, you get a dicyclic group. And that's generated by this matrix. And so this is the generalization of I to a 6th root, to an nth root of unity, and this is the matrix J. So this is a whole family of groups that I think has a lot of really neat properties that really gets swept under the rug. You know, if I give you this presentation, so most people are not going to see this presentation in an undergraduate algebra course. It might be if it comes up, it's buried in an exercise in the back, and that is not, and it's unmotivated. But if you see a picture like this, or if you see this representation, it helps. You can see why this is a generalization of the quaternions. Now, another way to see this, I really like this picture, is here are the 6 roots of unity around the edge here. So what if you take the quaternion group and you just replace, instead of I, you replace I, which is a 4th root of, I is the square root of -1, which is a 4th root of unity, with a 6th root of unity, and you just, and multiplication continues as before. So this complex number and J generate a group. This is the dicyclic group. You can do this for any even root of unity. And these families have, these groups have a lot of properties. They have an index 2 quotient, which is dihedral. One thing that I can, so here's why Cayley diagrams are so nice. You can see without even checking almost that this group is not only generated by R and S, but it's also generated by R squared and S. Let's check that. So so S takes me to these 4 nodes. If I do R squared to get up here, and then I do S, I get these 4 nodes. And then if I do R squared again, I get here, and I get these 4 nodes. So I can easily check that there's other generating sets. And if I give you the presentation like this, that's not obvious. You could get it, but it's something you would have to check, and it's messy, and you don't see it or understand it holistically the way you do with a picture like this. So again, this doesn't encode any more or less information as a presentation. It's just a very convenient way to see it. Again, think of like trying to teach calculus without graphing anything. You could do it, but why would you? So here's another way to lay out the quaternion groups. Here, going around the outside is like multiplying by J. So this is 1J, J in -1J cubed. and going inside or multiplying by omega. So this is, think of this as 1 omega, omega squared, omega cubed. And this highlights different structural properties of this group that the other one did not. Okay, so here's some groups you didn't know existed and others you possibly could, once you see them, you can't live without. This is a catalog that I liked growing up in the 90s. So there's, abelian groups, the dihedral group. I told you about the dicyclic group, but then there's these other ones, the semidihedral and semi-abelian groups. You may have heard this, you may know this by the quasi-dihedral name, but I don't think you know semi-abelian because a student of mine came up with this name. It's sometimes called a modular group, but it's uncommon enough that it doesn't have a name, but I think it absolutely belongs. And then we'll talk about the polygroup. And these groups, again, they come up in your favorite algebra books, buried as exercises or examples with these presentations. Now, what do you gain from these presentations? I mean, maybe if you're an algebraist, you see it, you understand something, but put yourselves in the shoes of an undergraduate student taking this for the first time. What are they going to get from something from like this, like say the subtle difference between this presentation and that presentation? Well, let me show you. So how do you generalize the dihedral group? So that dihedral group's got an element of order n over 2, or element of order n, I should say. And then it's got another element of order 2. So this is a rotation of order n and a reflection of order 2. So let me, and then these inner circles go this way. So what if I remove this inner circle and I say, how can I reconnect these inner red arrows? In other words, how can I what options do I have of replacing this relation with something else? Well, one answer is like this semidihedral groups. If you go, now this only works if this is the power of 2, but you go halfway across and then -1 to connect. So the red arrow internally jumps halfway across -1 and so forth. And so over here, it goes halfway across -1, takes you to here. And these are Cayley diagrams for this, for the semidihedral groups of order 16 and order 32. Now there's another option. Instead of going halfway across -1, you can go halfway across +1. So let me show you that. So these are called, or I call them semi-abelian groups after something that my student came up with. In Dumb and Foot, they call this the maximum modular group. There's a few other names that there's no standard one for this. And this looks very similar to that. Would you agree? In terms of the subgroup structure, they're very, very different groups, which is sort of tells you that the Cayley diagram tells you a lot, but it doesn't tell you everything. There's a lot of different facets of a group. And the Cayley diagram is really only one of them. And if I had more time to talk about subgroup lattices, I could tell you why these things are very different. Of course, there's one more way we can rewire this. If we put these inner red arrows this way, we get an abelian group. And I'm not going to define this. I just want to mention this in passing. For every finite group, you can draw what's called a cycle diagram that tells you basically all the orbit structure, the cyclic subgroup. So here's a 2 cycle or cyclic size 2 subgroup. Here's a size 2 subgroup. Here's a size 8 subgroup. Here's another size 8 subgroup. Here's a size 4 subgroup. This is for an abelian group. And it turns out that these 4 things that we've seen, the semidihedral, dihedral, semi-abelian, and abelian, these are the only 4 possibilities. And you can phrase this in terms of semidirect products and understand why this is the case. But that's a topic for later in the class. Now, these groups that we saw, the dihedral, semidihedral, and semi-abelian, here are the cycle diagrams. So a dihedral group has an element of order 8, and then there are 8 elements of order 2. So there's 8 size 2 subgroups. And for the semidihedral, you get an element of order 8, but you get also these cycles of order 4 and these 4 things of order 2. And the semi-abelian group remarkably has the same orbit structure as that abelian group. That's why I like the name semi-abelian. They have the same subgroup lattice structure, and they have a lot of other similarities as well. So this is tip of the iceberg. I'm happy to tell you a lot more about this if you want. So turns out there are only 4 non-abelian groups of order 2 to the n that have that big cycle around the outside. Here are the presentations. this is something, you can Google this and see a result like this, but this doesn't tell you very much. It shouldn't tell you very much. You should get, the Cayley diagrams really tell the story. And the Cayley diagrams are no more, no less than these presentations. Now, just for fun, there are ways to represent these groups with matrices. This is something that to me was new. And I incorporated this into homework problems because I had questions like, well, what happens if you do this if n equals 4 or 3 or 6 or something that's not a power of 2? These are things that I put on homework, and my students explore this. These are questions that normally don't come up in a standard undergraduate algebra course, but I think they are at least as important, not more, than spending all the time improving things like what I don't do in class is spend a whole class proving with this terrible notation that the symmetric group is generated by an n cycle and a 2 cycle. That's obvious. My mom understands that, and she never took beyond high school trig. If you think about seating arrangements, but you don't need to spend a whole day proving that. I would rather explore things like this. Now, I guess I spoiled what's coming next, but now there are other groups we can construct like this that are typically not done because the presentations are terrible. And one of them that I'm going to show you is this polygroup, which, how do you motivate that group without any visuals? It's not easy. So I don't think it's even really possible. So now here's the dihedral group. No, sorry. Let's take the quaternion group, which is generated by, let me make this a little thinner. So this is generated by I, negative I, 0, 0, and 0, 1, negative 1, 0. So this is Q8 generated by these. And let's take these 8 matrices and let's throw in this reflection, which is a you guys at the waiting room, you guys got it? Okay. Let's take these quaternions and throw in the reflection matrix from the dihedral group. Now, what this does is this swaps rows and this swaps the rows of a matrix or the columns depending on the left or right multiply. So if you do this, you get twice as many matrices and you get this group. And you can see the quaternions sitting inside here as an index 2 subgroup. I've highlighted those in yellow. So this is a beautiful group. You can see it's a semidirect product of, there's a dihedral group around the outside with Z2. It's also a semidirect product of the quaternion group, which you see right here with Z2. So you can see 2 index 2 subgroups jump out at you. Now, of course, this can be generalized. You can take, so what would happen if you take this matrix right here and you replace I with a higher root of unity? Well, if you do that, you get this group of order 32. So you get so we're generalizing and this is the poly group, it comes up in quantum mechanics in ways I don't really fully understand. I think somehow this is like a spin matrix. But maybe someone in the audience knows more about physics and can say a bit to that. So finally, the symmetric and alternating groups have a lot of very visually pleasing Cayley diagrams. This is called a Nauru graph that looks like the flag of the island nation Nauru. This is a Permudahedron. And so when I took algebra, I had homework assignments where I just computed a bunch of things in cycle notation. Just because you got to do it, get your muscle memory. So I don't do that for my students. What I do is I give them these Cayley diagrams and I say, label all the edges with elements in the symmetric group. And to do that, they have to practice cycle notation a lot. By the end of that assignment, they get really good at cycle notation and they end up with these pictures and they start seeing a lot of symmetries and a lot of patterns that they would not have normally. So everything in yellow, these are the even permutations. This is the appearance of A4 and S4. And these are not just the only 2 that I do. I also do these. Here, I don't tell them what the generating sets are. They have to figure this out. And they got to label these nodes with Cayley with permutations. So this is not a standard thing to do in an algebra course, but I think it's so much more helpful than just giving them a list of compute these permutations. And I'm doing this before we ever define things like subgroups or group actions or homomorphisms. We're really just exploring groups. We do this for probably over a month. And by the way, I have on the course website that I'll put in the chat, I post all of my slides, I post all of my homework assignments, and here are my homework assignments. I mean, here's what they look like. Here's I'll talk more about this in a bit. Every homework assignment has multiple pictures. And I provide a PDF of scratch paper with these diagrams with larger nodes and blank labels for them to label and turn in themselves. So they don't have to recreate these diagrams from scratch. So if you go to the course website that I will put in, you can explore all these materials. So this is a sort of, here's one I really like. Here are these 4 groups that I told you about before that have this index 2 subgroup, cyclic index 2 subgroup. And look how I label these nodes. So I call this 1A, B, C, and then negative A, negative B, negative C, and then same with X, Y, Z, negative X, negative Y, negative Z. And then I tell them to create a multiplication or Cayley table using things like plus or minus 1, plus or minus A, plus or minus B, etc. And this is a group of 8 elements, and figure out what group is it. This is a quotient. And for 2 of these 2, you get a dihedral quotient. And for these 2, you get an Abelian quotient. And so they are discovering what a quotient really is more than a month before we formally define it in class. So this is the sort of thing that you really can't do this. I mean, I guess you could make these tables, but you really get a holistic understanding by doing this using Cayley diagrams in a way that you cannot just if you do it purely algebraically. And if you think about it, why do we do it purely algebraically? It's because that's the book that I learned. I learned this from books that do it purely algebraically. These are books that are written by old white men at Ivy League-ish institutions who are writing them for the 19 or 20-year-old version of themselves, which is probably not the 19 and 20-year-old, which is probably not the same type of person that are taking my class. And it works for them, but it doesn't work for most people. It's not that accessible. It's not that inclusive. And it really pushes people, I think, out away from, algebra is a beautiful, beautiful subject. And Cayley diagrams are sort of the gateway into seeing that. And I think it's a travesty that all across the country, students take this class completely, without pictures, and they often don't enjoy it. It's this hard proof level course that they want to get away with it. So my homework assignments, I had a student tell me a week ago, this feels like doing a Sudoku puzzle. And a lot of it is. So the poly diagram I put, so I have them build semi-direct products. So here's, I'll talk more about this soon. So let me keep going. This is the alternating group A5, Doug Hofsteller, he's on the call, can you wave? He's got a bunch of really neat Cayley diagrams of A5 that he made years ago, which he sent me, and most of them I never seen before. So maybe we can, maybe be willing to share them later for anyone interested, or at least chat about them. So other things I do, I talk about left versus right group action. So this is the Cayley diagram of the symmetric group, and you can really think, and so I won't say too much about this, but yeah, I'm just going to put this picture and have you look at it and think about it. And I'm happy to share these slides with anyone interested. This is a special case of this is a Permudahedron in 2 dimensions, and I should say 3 dimensions. The 4-dimensional Permudahedron is a Cayley diagram of S4, and there's actually 2 different ways to label the vertices canonically. One of them is the permutation ij means you swap the ith and the jth coordinate over here, but over here it means you swap the I and the jth number no matter where they are. So this is technically a right action versus a left action. So we play around with group actions before we really formally define what an action is. So again, I'm mostly just sort of want to err on showing you more things and giving you less details. I'm happy to stick around and chat about any of these things that you want to, or send you more information. We talk about Freeze groups. So this is a Freeze group is a discrete group of, it's a symmetry group of a one-dimensional repeating pattern that has discrete symmetries. So here's the so-called largest Freeze group, and here's the Cayley diagram. And so on homework 1, I give this to students and I say, so think about what the symmetries are. There's 180 rotations about these points. There's 180 rotations about these points. There's horizontal reflections about around across the diamonds or across these gaps. And then there's the vertical reflection. And I have the students label all of these nodes. So let's call one of these the identity. And then I have them label all of these nodes with these different reflections, like it, and they see patterns about where the reflections and where the rotations are sitting within this Cayley diagram. And they start out the class seeing those. Now you can ask, what other frieze groups are there? Well, if you remove half of those diamonds, you eliminate the vertical symmetry, but now you have a different frieze group. And here you can see the relation GH equals HG inverse. This is much better to see than a long presentation. Here's the Cayley diagram. Now there are other ways to change that frieze. You can remove the other, so you can eliminate the vertical flip and all rotations, and you get this Cayley diagram, or the vertical flip and all horizontal flips, or you can eliminate both of the horizontal and vertical flips, and now you get an abelian group. So I know I'm going quickly, but again, I just want to show you, I call these things shiny objects. Now, we gotta be careful. You can't, it's tempting to want to just define a group with a Cayley diagram, but unfortunately you can't do that. And here's why. This is a group that I've done twice. This looks like a group. I say it looks like a group, it quacks like a group. It's not a group. If it were a group, it would be cyclic, because this red-blue path generates red, blue, red, blue, red, blue, red, blue, red, blue, red, blue, red, blue. It has order 10, but this is not an abelian group. So, but it still describes a group. I've drawn it twice, and I've labeled the vertices, the inner vertices, two ways. So this is SRQ. This thing here is SRRR, but it's also RS. So in whatever group is described by this, these have to be equal. Those have to be equal. You get this presentation, and that ends up being a group of order 2. So this, unfortunately, is not a group, and there's technical reasons for why that's not. But basically, the takeaway that I want you to have is you still need the formal definition of a group. This does not replace the formal. I mean, we still have plenty of proofs in this class, but it's just not entirely proofs. We use these visuals throughout. Okay, so thus far, I've spent half this talk, more than half the talk, giving you examples. But what I want to show you now is concepts that you may know and love, things like cosets and normalizers and conjugate classes and quotients, other things that you may not realize how beautifully encapsulated they are with Cayley diagrams. So we'll start with cosets. Now, a coset, there's obviously left and right cosets, if you know about these. So a left coset, so here's an example. You first do R, and then you do, so H here is going to be this subgroup. So the left coset RH, you do R, and then you do the paths in H, and you get these two. The right coset is you first do the H paths, and then you do R. Notice that these are different. Left cosets and right cosets need not be the same. So what I like to, so the cosets partition the group, the left cosets partition them this way, and the right cosets partition them this way. And notice these partitions are different. Now, what I like to do is I like to color each coset blue if the left coset is a right coset, and red otherwise. And the normalizer is just the union of the blue cosets. That's the normalizer. And you can, I remember learning about normalizer when I was, and I forgot what it was like a month later, because it's this algebraic definition, but my students are not going to forget what this is. It's the blue cosets. Now, why is it? Now, in terms of a Cayley diagram, the normalizer, so here's a sort of a cartoon of this, but the normalizer are the cosets that you can, here's the subgroup itself, that you can get to unique from the subgroup uniquely. So this coset I can get to via R, or via R to the 5th. This coset R squared, or R to the 4th. But this coset, the only way to get there from here is R cubed. So that is in the normalizer. Now here's one of my favorite pictures. So this is one of my favorite example groups, A4. Here are 3 different ways to draw the Cayley diagram, highlighting different groups. This is a group N, so this is N, H, and K. And you can see N is normal because all of the cosets, all of the left cosets are right cosets. H, I like to say, is fully unnormal because the subgroup itself is always going to be blue. But in this case, nothing else is blue. It's the worst possible outcome. Everything else is red. This is fully unnormal. And over here, it's sort of in between. You got these 6 cosets. 2 of them are blue. more than the minimum, but less than the maximum. So I call this moderately unnormal. And I can talk to you later about why I think these terms are really nice to have. I use them in CELO theory and many times throughout the course. But here's what I want you to notice from this. Look at these numbers: 1, 4, and 3. See what they recognize? This is the proportion, the inverse proportion of the number of blue cosets. So 1 out of 1 cosets are blue, 1 out of 4 are blue, and here 1 out of 3 cosets are blue. Remember those numbers, 1, 4, and 3? What else does that count? That counts the number of conjugates of A. So N has 1 conjugate, H has 4 conjugates, and K has 3 conjugates. This is just a special case of the orbit stabilizer theorem. But I show it before we ever get to group actions. And I don't prove, I save the proof to later, but it's something you could prove directly. And in my book, I put it as an exercise. One way to think about this is the wider this fan is, the further away from being normal the subgroup is. So the number of conjugates is a way to measure how unnormal or normal a group is. And the side index of the normalizer also measures how close or far from being normal a group is. And these are actually measuring exactly the same thing by the orbit stabilizer theorem. So this is a picture that, again, I cannot live without this picture when it comes to normalizers and conjugate classes and group actions. So speaking of conjugate classes, in terms of Cayley diagrams, let's see what so let's take, this is a group. It's a, I think what is it? It's a semidirect product of C4 and C4, it doesn't matter. But let's consider this subgroup A, and let's look at the conjugates of A. So a conjugate, so B, A, B inverse, you first do B, then you do the A arrows, and then you do B inverse. So you do the blue path, the red path, and then you go backwards blue to end up here. And you can check that for this conjugate, if you do blue squared, red arrows, and then backwards blue squared, you also end up back here. If you do blue cubed, red arrows, and backwards blue cubed, you end up back here. This group is normal. All of the conjugates are itself. In contrast, this subgroup, if you try that, if you do a red arrow, blue paths, and then backwards red, you end up here. That is not a normal subgroup. So this is a way to visualize conjugate subgroups in a way that you normally do not do in an algebra course. And for me, as an instructor, the story I like to tell is I thought I understood all of undergraduate algebra 2 years ago. I was like, this is something that I know very well. It's not that. And then when I started writing this book and coming up with these visuals and filling in all the gaps and finding these polygroups, semidihedral groups, et cetera, or semidicyclic groups, it was like being colorblind and putting on glasses and seeing color for the first time. I was like, oh my God, I did not realize how beautiful the landscape really is. And I was like, pushing 40 years old, having taught this class many times, thinking I knew everything, at least at the undergraduate level, and how wrong I was. And then I'm thinking, yeah, so let me continue with this. So if you do the same thing so this conjugate, double red, blue arrows, and then double red backwards, you actually end up back here. So this is actually in the normalizer of this subgroup, but this one is not. So this is another way to see normalizers to set up. So here's a left coset that's also a right coset. Okay, so remember that dicyclic group? Another example I like about this is centralizers. So centralizers, normalizers, I remember these from, I forgot the definitions when I was a student. They were algebraically subtle, but let me take S. So S is this blue arrow. This is like J. And what commutes with, or actually, let me start with R cubed. So R cubed is central. This is like -1 in that group. If this is 6 root ET and this is J, this commutes with everything. So this obviously commutes with the cyclic subgroup that it generates, but it also commutes with all of the cosets as well. So this is truly a central element. It commutes with everything. Let's look at R squared. What does R squared commute with? R squared commutes with, now let me do this one first, S. S commutes with only, obviously, every power of S, but that's the only thing it commutes with. So this is, I call this fully uncentral. It commutes with nothing more than its cyclic subgroup. Whereas R squared commutes with its cyclic subgroup, but it also commutes with this coset as well. I call this moderately uncentral. So see these numbers 1, 2, and 3? Those are also the size of the conjugacy classes. This has a size 1 conjugacy class. This is in a size 2 conjugacy class. That's in a size 3 conjugacy class. Also the orbit stabilizer theorem, but this is something that I can really, but I think it really makes the connection clear in a new way, and the Cayley diagram is central to this. So quotient groups. A quotient group is a way to collapse a subgroup, and this works if it's normal, and it doesn't work if it's non-normal. You can really understand what well-defined this is a hard concept to impress upon undergraduates. They struggle more than I would expect. And these pictures, really, I hear a lot of ahas when I show these pictures in ways that I do not when I just used to do things mostly algebraic. Here's the first isomorphism theorem. Any homomorphic image is a quotient. So here's a quotient, or here's a homomorphism from the quaternion group to the Klein 4 group. And what you're really doing is collapsing the Cayley diagram via a normal subgroup and then just relabel it. Now, here's another way to see it via Cayley tables. Again, my other talk has a lot more of these in it. I'm putting a couple of these things in here, but I think I've also heard a lot of ahas from this as well. Now, one of my gripes, I'm only going to talk about one of the other of the homomorphism theorem, is that every book has them in the wrong order. So the second homomorphism is this diamond theorem. That should not be the second one. The first homomorphism theorem says all homomorphic images are quotients. So the thing you should be asking, the next natural thing is, what the heck do we know about quotients? What do we know about the structure of quotients? Namely, what can we say about their subgroups? And well, the answer is, so this is normally the fourth isomorphism theorem, but it should come next. The subgroups of the quotient are simply quotients of the subgroup. Here's that dicyclic group. Here's that subgroup that I'll generate by -1. And if you quotient out by it, here is the Cayley diagram of the quotient. You can see here, this is D3. And we know this group. I've been doing this group all class. Here is a subgroup of D3, consisting of the rotation. In class, I call these shoeboxes. So this is here's 6 shoeboxes. This is a subgroup of 3 shoeboxes. If you take the lids off, here they are again. And if you take them out of the boxes, here they are. This shows that the one-to-one correspondence between subgroups of the quotient and quotient of the subgroup. Did I say this right? Subgroups of the quotient and subgroups of the original group that contain this. And so here's another way to see this via, here's the lattice of the shoeboxes. Here are the shoeboxes with the lids off. And then here's the original Cayley subgroup lattice. And what we're basically just chopping everything below here. So the quotient, you can see it sitting here like a stalactite, or stalactite. Okay, so automorphism. If some of you I recognize from my other talk, these are slides I did not put in my other talk. Automorphisms are, I define this, are basically rewirings, structure-preserving maps from a group to itself. They're just rewirings of the Cayley diagram in a way that preserves the structure. So here's 2 different Cayley diagrams. Here are the 6 automorphisms of D3. They, of course, form a group. Here's the Cayley diagram of the automorphism group, and here's the Cayley table. One of my homework problems is I tell my students, do this for D4. And I give them blank paper. Actually, I don't think I have time to do this, but I'll show you later if you want. So here's, of course, using the other Cayley diagram. And here's V4. Here's the 6 rewirings of V4. It's not hard to see that this is a non-Abelian group. Here is the someone in the waiting room. I'll admit them. Here is the Cayley diagram of that. And now I do this later in the class, but I start with, before I ever do, so I do this after we do homomorphism, but before we ever get there, early on, I talk about automorphisms of cyclic groups. And these are just rewirings of a single cycle. And it's not hard for the students to see early on that this only works if the number of things you skip is relatively prime to n. So for Cn, the automorphisms are generated by what I call the tripling map. So this phi sends a red arrow to 3 red arrows. So this red arrow, if you triple it, it goes to here, and that tripling map. So if you triple twice, now let's triple this red arrow. So this goes to 1, 2, 3. Sorry, that's 1, 2, 3. That gives you this. Now, if you triple this 1, 2, 3, that gives you this. So the tripling map generates everything. Here's the Cayley diagram for this. And this is how I construct semidirect products before we even formalize what a subgroup is. So a semidirect, this is the smallest non-abelian group of odd order. You can see, so these rings correspond to these things right here. Formally, this is a map from C3 to the automorphisms, which, in other words, just you're labeling C3 with these three things going right here, and then you're connecting things up as you would normally. Now, I usually call this, so A semidirect product B, and A for automorphism and B for balloon. And let me show you what I mean by that. So I realize I'm almost done, but remaining slides should be fairly fast. We also started about 5 minutes late, so hopefully you guys are okay if I go 5 more minutes. So C5 and C4, early on in the course, we construct the semidirect product between these two. So here's how we do it. Here's the automorphism graph of C5. So C4, the second thing, I call this B for balloons. So imagine taking this Cayley diagram, blowing up the nodes into balloons, sticking in rewired copies via this automorphism, and this is what you get, and then connecting them across. So you do this via a labeling map. This is a semidirect product. This is a visual way to, if you get a chance, go to the Wikipedia page and look up semidirect product. Look at the algebraic definition. It is a nightmare. How do you explain this to motivate it to undergraduates? I mean, if you're an algebraist, you get it, but it's really hard to impart that knowledge. Why would you do it that way when you can do it this way? Now, let me show you a different. So this map, notice, look at the exponents, 0, 1, 2, and 3. Another map is 0, 2, 0, 2. That gives you these rewirings and a different semidirect product. Early on in the class, I think homework 4 or maybe homework 5, I give students these two groups and I tell them to investigate. They discover that one of them has an element of order 10 and the other one doesn't. One of them has one element of order 2, the other one has 5. And you can do that by find a path in here that has order 10 or order 2. And then they discover that one of these has they construct a subgroup lattice and they realize that one of them has a dihedral subgroup, D5, and one of them has a dihedral quotient. And they discover that before we ever get to homomorphisms. Now, semidirect products, I can't talk about these without looking at subgroup lattices. You can characterize a semidirect product in the subgroup lattice by taking two groups that join up top and meet down at the bottom. So here's a cyclic group, C8 and C2, that join up top and meet at the bottom. Here's those groups highlighted in the Cayley diagram. You also have a quaternion group and a cyclic group that join up top and meet in the bottom. Here is that highlighted in the Cayley diagram as well. And here's a little different way to draw that. So these are examples that I do in class, and my students get used to this. And so here's the dicyclic group, or a generalized quaternion group. If you got a power of 2, it's not hard. So you can see right here that there's no way you can get two subgroups whose intersection is trivial. This is never a semidirect product of two of its subgroups. It's not hard to see that any element in this Cayley diagram, if you iterate itself, you will eventually run into -1. So any two subgroups will contain this subgroup as an intersection. So this is never a semidirect product. Good luck trying to, this is something where without the pictures, it's not a fun thing to show. Here you can almost see why it's true using this Cayley diagram and this subgroup lattice. Okay, so I'm just about done. Group actions, I'm going to flash the last couple slides. This is not how you should teach group actions, purely algebraically. It's said that to understand a group, you really should understand its actions. How do you motivate that with a definition of group and then this crazy definition of, I understand this definition of action, you probably might do too, but how I describe group actions as, so this is the last concept I'll introduce, a group switchboard. So imagine, so here's my favorite example. You got a set of elements, and every element of a group has a button. And here's the rules. When you press the A button and you then press the B button, that's the same thing as pressing the AB button. So here, the R button is what you get when you follow the red arrows. The blue button is what the F button is what you get by following, sorry, the blue arrows. And then the RF button is what you get by following the blue path and then the red path and the blue path. That's all that so this is like a generalization of the Cayley diagram. And now the statement of to understand a group, you should understand its actions really is just saying to understand a group, understand all possible action diagrams. And I'm not going to go into details on this, but given any action like this, I like to draw the fixed point tables. And you can read things like the stabilizers right off of the columns. You can read the fixed point sets right off of the rows. The kernels are the rows that have only check marks. And the fixed point, global fixed point sets are the columns that have only check marks. And the average number of fixed points per row is just the number of orbits via Burnside's lemma or the orbit counting lemma. So let me flash some pictures with you to finish. Conjugacy classes. These are the conjugacy classes of D6. I find it so much more helpful to see this picture than to just write down algebraically what the conjugacy classes are. And given this, you can look at the fixed point table and you can see the kernel are right here. The fixed point sets are right here. And the orbits and the stabilizers, you can get them as well. So this is like a generalized Cayley diagram. Here's a subgroup lattice of A4. Here's the conjugacy classes. This is a much better way to visualize what conjugation really is doing, why this is normal and why this one is not. You can come up, here's the table you can construct. Here's if you let a group act on cosets by multiplication. Well, this, as we saw, is not a normal subgroup. You cannot quotient out by it and get a group. But if you act on it by multiplication, you get this action or generalized Cayley diagram. And this is the action. So this is what happens when you collapse this by the right cosets instead of the left coset. So I have my students construct this sort of thing for other groups in class that algebraically they would just be too complicated and not unmotivated to do it. Okay, so here's I think my last example involving automorphisms. Here are the inner automorphisms of quaternions on itself. Here are the outer automorphisms. You can overlay them to get the full group. You can collapse by the conjugacy classes to get to get the action of this on the conjugacy classes. And this ends up being a semidirect product of these. Here's a picture of automorphism. So you press the R button, this is what happens. When you press the F button, this is what happens. Here's an outer automorphism. So when you do this, so when you press the F button and then this outer automorphism, this is the permutation that happens. So I have my students create this for a different group. And I hope you'll agree that this is so much more effective at getting them to really understand automorphisms and actions and subgroups. So here's that same example on a Cayley diagram and on a subgroup lattice. Again, I don't need to spend time going into details, but that's basically all I want to show you. In the closing remarks, in 2005 and also 01 and 07, Doug Hosteller, who's in the audience right now, he taught a course at Indiana University called Visual Group Theory. And he sent me a bunch of emails, which are really fun to read, about sort of the history of how this developed via sabbaticals and via classes. And one of the students wrote this book, Visual Group Theory, with the same name. And that's what got me to explore this in more details. Stephen Strogatz, many of you know, called Nathan's book the best introduction to group theory or any branch of higher math he's ever seen. And so what I'm working on is my goal. I'm not trying to sell my book. I'm trying to sell an idea. I think every algebra course maybe doesn't have to use these Cayley diagrams as much as I do, but they absolutely should be a fundamental tool to learn and to understand and explore groups, because this is a beautiful, beautiful subject. And most students, from what I talk to, graduate, the ones who don't go on to grad school, which is like 95% of them, not really understanding why it's a beautiful subject. So this talk was mostly on Cayley diagrams. I'm happy to share other visuals that I use. If you are interested in teaching this way, I'm happy to share my LaTeX code. I want to make it freely available for everybody. Otherwise, it won't get taught this way. I post everything for free on my website, and other things. I'm open to ideas. If you have new visuals applications, I was talking to a colleague of mine about applications of PDEs and Fourier series that I'm not aware of involving groups. So if you're in a math ed and you want to explore the pedagogy of this, let me know. But I will give you the warning, once you see these visualizations and you teach algebra, you really can't unring that bell. You cannot go back and teach it without these visualizations once you see them. So I like to say that this is sort of like choosing to take the red pill in the Matrix. So I invite you, if you're interested in this, to take the red pill, and also tell you it's so much more fun to teach this way and to meet students and chat and office hours with these visuals, with Cayley diagrams, than it ever was without it. So thank you for your attention. I'll stick around as long as you guys want if you have questions or comments. And feel free to send me an email. Oh, let me put in the chat, this is my course website where I have all of the materials online, including the homework assignments and slides. I can email you the LaTeX if you want.
Great. Thank you so much for the talk, Matthew.